Okay, before I move on to example 3, I want to go through the related rates procedure that I've come up with. This is for your basic problem. So again, if the problem looks like one of those two, just go ahead and do it. All right? But usually a related rates problem relates back to a geometry problem. And everything you ever learned about geometry, and I'm talking about shapes, rectangles, circles, squares, triangles, cones, pyramids, surface area, volume, anything involving these figures is going to be important. Okay? The very first step of a related rates problem is to draw a picture. You do not have to be a professional artist here. Draw a picture. If it says square, draw what looks like a square. If it says circle, draw a circle. All right? Give me a picture that represents what's happening in the problem. And use a variable to represent the distances of all moving dimensions. That's very important. They're going to tell you stuff. They're going to say the car was 30 miles away, but it's moving. All right? So instead of writing 30 on your picture, write a variable to represent that distance. And then let's say you call it x. And then down here put x equals 30. Make sure x is on your picture. Anything that's changing in your picture has to be related to, or has to be identified as a variable in your picture. All right? Even if they tell you the exact value. All right? Determine an equation relates all moving variables. This means that any equation from geometry that's true can be used. If you have a right triangle, the Pythagorean Theorem is allowed. All right? If you have, let's say, a triangle, area is equal to 1/2 times base times height. If you have a cube, volume equals length, or whatever the dimension is, cubed, right? Surface area is 6x squared. All these formulas that we can come up with specifically about these figures. So any geometric figure or property that you've come up with or that you've learned throughout the years is allowed to be used to relate the variables. That's what step 2 is. That represents what I consider to be the hardest step. What relates to variables? So everything that's moving has some variable related to it, and something relates all those variables together. You have to come up with that equation. All right? Then you write down specific values of each dimension, specific value of all rates. And again, if there's 2 rates, you're going to have 3 variables. If there's 1 rate, you'll have 2 variables. If there's 4 rates, I hope you never have that one, but there'll be 5 variables. That'd be ridiculous. The worst we get is 3 variables. But if let's say there's a car, and let's say they're approaching the same intersection, they both have a speed, right? The distance between the cars is changing also, so that's the 3rd speed. All right, that's kind of what we're looking at here. So you should know everything except for 1 rate. Differentiate, and then from that point on is what we just did the rest of them. Differentiate with respect to time, substitute everything you know, solve what you're looking for. Last 3 steps is what we've done in the last 2 problems. The first 3 steps is new because we have to determine the equation. All right, so a plane flying horizontally at an altitude of 2.5 miles and a speed of 800 miles per hour passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 4 miles away from the station. So, let's take a look at the picture here. There's my radar station. Hold your amazement at the wonders of my artistic ability. That's my radar station. In order to make it more clear that it's a radar station, I'm going to put RS next to it. That's for radar station.
Ooh, nice.
Okay, now, we know the plane's flying horizontally at an altitude of 2.5 miles and a speed of 800 miles per hour passes over. So at some point it passes over this radar station, right? So at some point, that's where the plane was. There's my plane. I know it looks a lot like the radar station, but now it looks a lot more like the plane because I put a P next to it for plane. I might even say plane. Which direction is it flying?
Due east or horizontally.
Horizontally, east or west, doesn't matter. All right, but horizontally is what matters. Now, altitude of 2.5 miles. So I know that this distance here, without a doubt, is 2.5 miles, right? And if the plane is flying horizontally, that altitude is never going to change. So that's why I put a number on that. Okay, so again, it's up to you when you're drawing this picture. Ask yourself, is this dimension going to change or not? Is the plane going up or down, or is it going flat across? In this case, it said horizontally. Horizontally means in one direction, not moving up and down. So it would look like this. There's the plane. All right, he's flying that way.
Nice.
All right, now, obviously, he's flying this way. He's moving, right? So that dimension is changing. We call it something. I'm going to call it x.
call it?
You can call it D for distance, you can call it A because you like the letter A. It doesn't matter what you call it.
What about a word?
I wouldn't go call it a word. Use a letter. All right. So that's one of the things. And if I just start writing over here, x equals y equal, or let's go D. I'm going to say D is the other very one. And then dx over dt equals, and d over dt equals. All right. So I'm drawing my picture, but in the midst of drawing my picture, I can actually start identifying some of these things. Because, again, I got to put variables on my picture. That's required. All right, but if I know what a variable equals, then I can go ahead and put those in, right? All right, so the speed of 800 miles per hour, what would that be in terms of all the four of these things?
dx over dt?
dx over dt, very good. These are always speeds. Okay, look at the picture. Is x getting bigger or smaller as the plane flies off in the direction it's flying off?
Bigger.
Bigger. Even if it was going that way, it's getting bigger, right? All right, so the radar station is where it is. The plane, when it passed over, is right there. It's flying away from the radar station, so the distance between the vertical position of the radar station to where the plane's going to end up eventually is getting bigger. So this is a positive 800 miles per hour. Okay. The other thing we have to establish here is the other changing distance. The distance the plane is from the radar station itself. That'd be this thing here. When the plane's right here, he's exactly 2.5 miles away from the radar station, right? Because he's right overhead. Okay. This stays 2.5, but as he goes off this way, this is increasing, right? It was 2.5, but as he flies away, this is getting bigger. And I've decided to call this D. All right. What does D equal? For? How do we know that?
It says for when it increases when it is 4 miles away from the station.
When it's 4 miles away from the station. It's not saying it's 4 miles here, but it's 4 miles away from the station. Here's the plane, there's the station. Distance from the station is 4. So I can put D equals 4. So again, D is changing, right? That plane's moving, so D is changing. D in the picture, D equals 4 over here. All right? Do they tell us what X is? No. Do they tell us what dd over dt is?
No.
All they've given us is these two numbers. All right? So now it's up to us to apply geometry. Some geometry stuff we've learned. Would everybody agree with me that this is a right angle?
Yeah.
Absolutely, right? And if I'm looking at a right triangle, what is a property that's always true in a right triangle?
It's 90 degrees.
90-degree angle. Anything else that might be more helpful to us in the working of this problem?
C equals c squared.
The Pythagorean Theorem. Leg squared plus leg squared equals hypotenuse squared. And based on this picture, the right angle is here, the hypotenuse is opposite it. So I know that x squared plus 2.5 squared, which is 6.25, is equal to d squared. That's what step 2 of your process is. Write an equation that relates to variables in the problem. The only things that are changing in this problem as far as distances are concerned, the distance the plane travels horizontally and the distance the plane is away from the radar station. Everything else stays the same, right? So we have these two variables. This equation is a true statement of fact that relates to two variables in the picture. Again, that's what step 2 always is. Is there some equation out there that we can write that will truly represent all the variables in the problem that's true?
You can't put 4 in?
Not yet.
Not yet.
Again, when you write this equation, your equation is based on the picture. Your picture has variables representing things that are moving. The exact numbers happen after you differentiate. Okay, this is after you differentiate. We'll put a protected box around it. That doesn't matter. It matters in the whole context of the problem, but when we're doing step 2, all that matters is our picture that only has variables representing things that are moving. All right? Now, if you take a look, I'm missing x, right? Does everybody see that if d is equal to 4, I can figure out what x equals? So I have the ability to find out what x equals. Sometimes you need it, sometimes you don't. So here's my thought. I'm going to find out what I can from the words, stick it over here. If I need more information, I'll go back and find that information when I need it. All right? There's no reason to make a calculus problem uglier than it has to be. So at this point, once I get my relating equation and I have at least most of this filled in, I'm ready to go. All right? So what's the derivative of x squared?
2x.
2x. And I got to put a dx over dt because it's not t. By the way, it'll never be t. Don't ever put t for a variable. All right? T is out. All right. What's the derivative of 6.25?
0.
0. All right, 0 times anything is 0, so it just goes away. Derivative of d squared?
2d
2d, and then we'll put a dd over dt. Some people don't like to use d because of the dd over dt. It gets kind of monotonous or whatever, but I don't know. I can handle it, so I'm going to go ahead and keep on with it here.
Keep on keeping on.
What I want to find out is what dd over dt is, right? So that's what I'm looking for. I need to know the values of d, dx over dt, and x. D, dx over dt, and x. I don't know x, right? So again, I have the capacity, though, using this equation. The specific moment in time we care about is when d equals 4. So if I take my equation, x squared plus 6.25 is equal to 16. That means x squared is equal to 9.75, which means x is going to equal the square root of 9.75. And get out my trusty calculator here. Square root of 9.75. My calculator says it's 3.1225. As it's been since geotrig for you guys, as a general rule, if you're going to approximate in your work, go 4 decimal places. That way your 2 decimal place approximation for final answer is going to be pretty accurate. Okay, this would be the situation Tyler was asking about. Do we put d equals 4 in the picture, or d equals 4 right here? We only have to do that if we have to figure out what one of these other variables equals. So 3.1225. So at the specific moment in time that we're exactly 4 meters away from, or 4 miles away from the radar station, the plane has flown exactly, or approximately 3.1225 miles horizontally to make that happen. So if I substitute everything I know in at this point, before I do that, notice there's a 2 on both sides. That is legal. And more often than not, when the Pythagorean Theorem is your relating equation, that's going to happen. A bunch of 2's, they'll all cancel out. Because everything has a square on it, you're going to bring the 2 down and everything. So that's not uncommon. X equals 3.1225. dx over dt is positive 800. D is equal to 4, and dd over dt is what we care about. All I got to do to get the answer is divide everything by 4. And then again, it's just a matter of using a calculator. 3.1225 times 800 divided by 4 is 624 and a half. Notice the number here came out as a positive number, okay? The speed was positive for x, right? And notice d is increasing, and we got a positive speed there also. All right? So 624.5 miles per hour is the distance change here. Obviously the plane's not flying that direction, but if you're here and the plane's here and you want to know how quickly you're getting away from that person in the radar station, that will be the speed at which you're moving in that direction.